Here is an example how to run a one-way ANOVA in SPSS. We see we're just going to use this factor here. These are the children that have a math test, and we wanted to see if the levels of the education of their parents is they have different means depending on the levels of the education of their parents. So our factor is education of the parents, and the dependent variable is math. We're going to go into Analyze, Compare Means, OneWayANOVA. As a factor, we choose highest education. This factor has 3 levels. And we choose math total as dependent variable, and we have it up here. Then we could run this and see if the ANOVA is significant, if there is a difference in variances between groups and within groups. But because we were going to do it in one run, we already asked for the means comparisons, and we'll just pick the Sheffy. You can also, if you the LST, you can also pick it will be a little bit less strict. Then for the options, we choose the descriptive statistics and the means plot. Hit continue and OK. Here we see the syntax, what it did, and we see an overview of the means for each of the groups. So no education has a mean of 29 in the test, undergraduate mean of 32, university degree of mean of 36. And we see that we have most people in the lower education, 56, some kids in the undergraduate, 32, and very few at the master's degrees or postgraduate degrees, 12. Now here we come to our ANOVA table. This is what we're really interested in. It tells us, is there a difference between the groups? So we get the within groups mean squares and the between group mean squares. When we divide, how we expect, if there was no difference, we expect the mean squares between the groups to be about the same as the mean squares within the groups. Here we see, and then we do the F ratio. F ratio is just between groups divided by within groups, and this is 7.18. So 7 times almost 37 here gives us about 271. And when we test the probability of this happening, although in reality the null hypothesis is true, we see that it's highly unlikely that there's no difference, that we get this result of a difference, and there's actually no difference in the population. So we said, okay, if we hadn't done it yet, we would say we need to do post hoc comparisons. We need to test out the means of each group against each other to see where those differences coming from. So this is what the next table is all about. Those are the post hoc tests, and we do multiple comparisons. So we do all these mean comparisons at the same time. That's a better way to do it than having individual t-tests between each group. This is a test that runs all these comparisons at the same time. And why is this better? It's better because we don't have an accumulation of the alpha error. If we did an individual t-test 3 times, with each time we'd have 5% potential error, right? If we add this up for each of the 3 tests, we'd have 15% error. Right here we still remain at the 5% level, but we do test those differences a little bit more strictly. So what does this tell us? We see we're comparing the first group with low education with the second group, undergraduate, and we see there's a difference in the test of about 3 points. So their score minus the undergrad score is -3. So the first group is 3 points lower than the second group. And if we go over, we see, okay, this is not statistically significant. So higher than 0.05. So although there's 3 points different, the difference is not statistically significant. The next line, we compare the low education group with the university group. There we see there's almost 7 points difference, 6.9. This difference here is statistically significant. The significance level is below 0.05. So we can say that statistically we are pretty sure that there is a difference in the population between the children with parents with lower education and children with parents with an higher education degree. So then here we repeat the first comparison, undergraduate and no education. We had that already up here, but now you can see, because we start with the undergraduate, we take their score and we subtract the lower education score, which leaves us 3 points. But it's exactly the same thing. It's the same difference, the same standard error right here, and therefore also the same significance level. So this is basically the same result. What is new here is the undergraduate, comparing them with the higher education. And now these guys, we see there's a difference. If we take their score minus the university score, we get a negative value, minus 3.8. So we know that the undergrad score is lower than the university score. So if we test that for statistical significance, we found out that it's not statistically significant because this significance level is higher than 0.05. And then the last box, we actually looked at this already, right? There's university versus no education. We had this up here, and university versus undergraduate, we just did this right here. So these results repeat themselves after 6.9, the minus 6.9, the 3.8, the minus 3.8. And again, the significance levels are the same what we found before. It's just that the sign changes. So what did we learn? We know that no education is different from university, but undergraduate is not different from no education, and undergraduate is not different from university in statistics. And then what we see here with the graph, we can say, okay, these guys, these very low guys, are significantly lower than these guys, but they're not lower than the middle group, and the middle group is not lower than the higher group. So that's the one-way ANOVA.